Okay, so you've been doing stoichiometry for longer than you think, and you actually started doing stoichiometry way back in chapter 3. And what you were doing at that point was what we call composition stoichiometry. So it's just the stoichiometry of individual elements, or elements in we moved on to elements and compounds in chapter 7. So the mass relationships of elements. If I tell you that I have 100 grams of carbon, how many moles of carbon is that? You can figure that out. That's compositional stoichiometry. In chapter 7, we moved up to compositional stoichiometry with compounds. If I have 100 grams of sodium chloride, how many moles of salt is that? So you've been doing this stuff. These are your GMA problems. What we move into now is reaction stoichiometry. So here we're looking at a chemical reaction, we're looking at the balanced equation, and we're figuring out how many grams of this will produce how many grams of that. Or if I need to produce this many grams of this stuff, how many grams of that stuff do I need? So this is real chemistry suddenly. Like suddenly you have enough skills to be doing some real practical functional work. And you're going to do my favorite lab of the year in here, in this chapter, and you'll look at making soap. And if I have this much available lye to react, how much fat do I need to react with that to make my soap? Okay, so all stoichiometry boils down to four problem types when we're talking about reaction stoichiometry. You can have both the given and unknown in moles. These are really easy one-step problems. Okay, I could train a chimp to do these in an afternoon. You'll all be able to do them in about 10 minutes. We can have problems where you're given something in moles and you're asked for an answer in grams or an answer in mass. We can flip that on its head and you can have a given that's in mass or in grams and be looking for a number of moles as an answer. And the last one is where everything is given in mass. Your given is in mass, and the answer that you're looking for is also in mass. Okay. So with each of these, you just add steps to the factor label. You know, these are a one step. These are both two steps, just reversed steps, and then these are our three steppers. So, okay. It all starts off with a mole ratio. This is the heart of doing any stoichiometry problem. So you're going to get really good at finding mole ratios. And all it is a conversion factor that relates the relative amounts, relative, because it's using the coefficients, of any two substances involved in a chemical reaction. So those coefficients that you've put in as your balancing are what you're now going to use to create mole ratios. So we have this equation. We have a reaction, and now that you guys have enough chemistry to sound not like little kids, but to sound like real people who are studying chemistry, you would say that you would read that as a sentence how? Maybe want to give it a shot? You want me to? Okay. 3 moles of potassium hydroxide react with 1 mole of phosphoric acid to yield 1 mole of potassium phosphate and 3 moles of water. So that would be a sentence. From that single equation, you can derive 8 basic mole ratios. We can look at the ratio between the potassium hydroxide and the potassium phosphate. And for every 3 moles of potassium hydroxide, we get 1 mole of potassium phosphate. Okay? And again, these numbers are just coming from the coefficient. If there's no coefficient, it's a 1. We can also flip that on its head. If we produced 1 mole of potassium phosphate, we know that we would have had to react 3 moles of potassium hydroxide. We can do the mole ratio between the potassium hydroxide and the water. And hey, look at that. 3 moles of potassium hydroxide reacted will yield 3 moles of water. Flip it on its head. If we need to get 3 moles of water out of this, we'll have to put 3 moles of potassium hydroxide in. What's the immediate impulse with that 3 to 3? Simplify, simplify, simplify. It's 1 to 1, it's 1 to 1. I would suggest strongly that when you're doing the mole ratios in stoichiometry problems, you actually don't simplify. There are some reasons that will become apparent as we go down the line, but I would really suggest not simplifying those. Okay, we can look at the ratio between the potassium hydroxide. Oh, there's a typo there, isn't there? That shouldn't be KOH, that should be phosphoric acid. Sorry about that. So we can look at the relationship between the phosphoric acid and the water, and that again gives us one that we can flip on its head. So we can look at that in either direction. Make sure you fix your notes on that. And we can look at the relationship between the phosphoric acid and the potassium phosphate. So we know that for every 1 mole of phosphoric acid that we put in, we're going to get 1 mole of potassium phosphate out, and vice versa. If we needed to produce 1 mole of potassium phosphate, we know we would have to run the reaction with 1 mole of phosphoric acid. Are there any relationships that we didn't look at? I should actually move that blue line up. That was... So which ones didn't we look at? We didn't look at anything between the potassium hydroxide and the phosphoric acid, did we? There's actually a reason for that. When we get a little bit further along in this chapter, we're going to look at we're going to look at stoichiometry that does involve that ratio, the ratios of the reactants to one another. So I kind of want you to make note of that when we start doing this, it's a different kind of stoichiometry. This is limiting reagents is what we'll be looking at that point. Okay. That's really hard to read. Limiting reagents or limiting reactants, either one. Those are the only kind of problems where we look at the ratio between the 2 reactants. Okay, so let's practice this. Oh, that's what we just did. Once we have that ratio, we can figure out how much product we're going to get out of a given amount of reactant. So the sample problem that I gave you here, if you're given 9 moles of potassium hydroxide, how many moles of potassium phosphate can be produced? This is a factor label. These are factor label setups. So what do you start every factor label ever with? First box. Your given. So our given here is 9 moles of potassium hydroxide. Remember how I've been saying you need to put in the units and the chemical because there's going to come a point when that's really necessary? This is that point. So you have to be very, very certain that you always list both your units and your chemical because you're going to have more than one chemical in that factor label. And if you just put in numbers, it's way too easy to lose where you are. So we've got 9 moles of potassium hydroxide, and what is it that we want to know? What are we looking for? Units and chemical. Moles of potassium phosphate. So again, just like every factor label we've ever done, what has to go in the next section down below? Well, it's the same units and chemical to cancel. So we're looking for things to cancel on that diagonal in the next box. So we know that the units are going to be moles and the chemical is going to be potassium hydroxide. whatever's going in that last box on top has to be what we're ending up in. Moles of potassium phosphate. So where do we get a mole ratio? Because what numbers do we put in there? Well, the numbers we put in are going to be our mole ratio, and those are going to come directly from the coefficients in the balanced chemical equation. So for every 3 moles of potassium hydroxide that we have, we're going to form how many moles of potassium phosphate? 1. So this one's the E, multiply across the top, multiply across the bottom, and divide. The math is pretty easy on this one. You can do it without calculators or anything else. How many moles of potassium phosphate are we going to get? 3. And that would be our final answer, is 3 moles of potassium phosphate. No need to worry about sig figs or anything else here. We'll pause now because the bell's going to ring any second. When you come back, you will have to have a calculator out. So that is a mole-to-mole problem. Easy, one step. Like I said, I could train a chimp to do those in an afternoon. You can all do them right now perfectly. I could give you a whole test of those and you would all get A's. So obviously we can't keep it simple. We have to pull molar mass into the whole thing. So we more commonly do problems that involve mass in one way or another. So we've got the same equation here, and we're saying that if we have 9 moles of potassium hydroxide and we get 3 moles of potassium phosphate out, what's the mass of potassium phosphate that we're creating? So we could set this up the exact same way as we set this up, and as a matter of fact, we'll just go ahead and we'll borrow this. Copy. Paste. Okay. So we've got that entire thing. I'll shrink this. Now all we have to do is add another step. So we want to end up in grams of potassium phosphate, K3PO4. We know that the box in the next space and down one, and I would actually, I would recopy yours to note that it's, the same thing with just an add-on. So what units and what chemical are we going to have down and below? Because the units and chemical always have to cancel. They have to cancel. So we're going to have moles of potassium phosphate. What do we want to end up in? Grams of potassium phosphate. So what's going to go in our top last section? Grams of potassium phosphate. Now, the $64,000 question, where are we filling the numbers in here from? Molar mass. So we have to use molar mass. To figure out potassium phosphate, you've got your periodic tables out. Potassium is what, 39.1? What's phosphorus? Who's got phosphorus? No, 30.97. Okay, and that's times 3, that's times 1, that's times 4. What do we get for a total? Who's got it? Okay, so we've got 212.27 is the molar mass of potassium phosphate. So where does that number go? Which box? Top? Top, okay. So we have 212.27 grams of potassium phosphate. What number do we put in there for moles? 1. Because the molar mass conversion is always going to be per 1 mole. What we are saying, this is a statement, that 1 mole of potassium phosphate is 212.27 grams of potassium phosphate. Okay, so now it's just a matter of multiplying across the top, multiplying across the bottom. What do you get? What's your raw answer? 636.81 grams of potassium phosphate. Oops, I already had grams there. Now, how many, ooh, this one's a tough one. How many sig figs do we have? Yeah, because we have to go back to our original given for sig figs. Our given was 1 sig fig. So, how would you express that with correct sig figs? .600 grams. Very, very imprecise. Okay, so you've done mole to mole. Now you've done mole to mass. What do you think's next? Mass to mole. We're going to turn this on its head. Okay, so given 175 grams of potassium hydroxide, how many moles of potassium phosphate can we make? So, as always, we're starting with our given. So our first box will be 175 grams of potassium hydroxide. And we know that we need what units, what chemical down in the next space. We know we need grams of potassium hydroxide. So let's step back a second. We know we want to end up in moles of potassium phosphate. To go from grams of potassium hydroxide to moles of potassium phosphate, we're going to have to do what? We have to go through a mole ratio. But to get to a mole ratio, we have to go from a mass in grams to a number of moles. How do we do that? We do a conversion into moles. So, do we have the molar mass of potassium hydroxide? So we have 39.1. 56.11. What anybody else is getting? Okay. So, where do those numbers go? The what? Bottom. So, 56.11 grams of potassium hydroxide is equal to how many moles? 1. Okay. Our last step, last box. Down to cancel. So, what units are going to go on the bottom? And what chemical? Potassium hydroxide. And what units and chemical do we want to end up in? Moles of K3PO4. Okay, where do we get our mole ratio? From the equation. So we have 3 moles of potassium hydroxide for every 1 mole of potassium phosphate. Multiply across the top, multiply across the bottom, and then divide. 1.039624547. Okay. All right, so we've got this crazy raw number. What would our final sig fig answer be? How many sig figs do we have, Madison? 3. So our sig fig number would be 1.04. Yeah. Oh, okay. I'm sorry. I thought you said 1.03. 1.04 moles of potassium phosphate would be our final sig fig answer. Okay. Now, here's the question I want to ask you. If I give you a lump of table salt, I give you a dish with table salt in it. You have no pencil, no periodic table, no calculator, and I hand you one of the balances in the back. Can you tell me how many moles of salt you have? No. 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 we don't have mole balances. Because a mole, our balances measure mass. And moles come from mass, but they're not mass. We can't directly measure mass. We have to calculate it. So, how useful do you think these mole-to-mole problems and mass-to-mole problems really are in the long run? Not very useful. Not terribly useful. So really what we do mostly are mass-to-mass problems. So let's do a mass-to-mass problem. We're going to use the same equations, and I'll give you a little problem-solving tip on these things in a little bit. Here's your question. 375 grams of potassium hydroxide reacts. What mass of potassium phosphate will be produced? So, same thing we start off every problem with, which is the given. It starts to sound like To the Bat Cave after a while. To the given, 375 grams of potassium hydroxide. And we know we have to have what down to cancel? Grams of potassium hydroxide. Now, we know that typically if we're starting with mass in any of these problems, our first step is to get into moles, because the relationship between the two chemicals is given in moles. So how do we get into moles? Well, we put moles of potassium hydroxide up there. Do we have the molar mass of potassium hydroxide? Yeah, we just did it on the last one. So 56.11 grams of potassium hydroxide equals how many moles? 1. Okay, so what units, what chemical, down and next to cancel? You got it. Moles, potassium hydroxide. Where are we going with this? What do we want to end up with? Yeah, grams of potassium phosphate. So we know that we need to look for a mole ratio between potassium hydroxide and potassium phosphate. So for the mole ratio, we go back to the problem. We have 3 moles of potassium hydroxide for every 1 mole of potassium phosphate. If we stopped right there, we would be in moles of potassium phosphate, but that's not what we want. So what do we have to put next and down to cancel? Moles of potassium phosphate. And what units in chemical are going to go in that last top box? Grams of potassium phosphate, K3PO4. Do we have a molar mass for this? Hey, look at that, we do. 212.27. Oops. 212.27. So now you've got some math to do. Okay, so we've got a raw answer of 472.888077. How many sig figs do we get here? 3. So our final will be 473 grams of K3PO4. Now, super important on these. Always give me a chemical. Always give me a unit. That could be 473 dirty socks, 473 blueberry muffins, 473 baby ducklings. I don't know what that is. So it's got to be 470. And if you say 473 K3PO4, that could be formula units, that could be moles, that could be grams. We have no idea what that is. So please make sure that you do that. I put up the first part of the Chapter 9 review assignment. Numbers 10 through 14, 16, and 17 are all practice problems for these sorts of things. I'm looking through my stuff to try to find another practice set. I had said FIP would be tomorrow, but I think it'll probably be Monday. Your labs will be due Monday, so we'll do some practice together tomorrow, and I'll give you a little bit of time. We'll have some discussion about your labs because I want to hear your thoughts on them. I'm going to pass back the multiple choice tests, and that's all I got.